So our compiler's textbook mentions two rules for a compiler. The first rule is that the compiler must preserve the meaning of the program being compiled. So it's not a good compiler if the program that it produces is different than the original program. So this, of course, raises the question of how do we define a program's meaning? And for most compilers, this is done by encoding that meaning using some sort of intermediate representation. So we don't go directly from the source language to the target language. We go from the source language to one or more intermediate representations, and then finally to the target language. So there are a lot of different kinds of intermediate representations. We're going to study a couple of these over the course of the semester. So there are tree and graph-based IRs like abstract syntax trees or control flow graphs, and there are also linear intermediate representations with things like register transfer language, Java bytecode, or other intermediate languages like iloc or y86. Although y86 is also a target language as well. So this then leads us to sort of the standard compiler framework, or I'll say sort of the historical compiler framework, in which we separate the front end of a compiler from the back end of the compiler. So the front end is understanding the program, so taking the source language and building the intermediate representation. And then the back end is taking that intermediate representation and then converting it to the target language. And the primary benefit of separating these two is that now we can retarget to different languages or architectures very easily. So for instance, once we have a back end that generates, for instance, to x86, we can extend our compiler to support new languages simply by writing a new front end. We don't have to write the entire compiler again if we want to add a new source language. Same for the backend. If we want to target a different machine ISA, for instance, we can just implement a new backend and we don't have to do the entire compiler over again. So in a modern compiler framework, we're tending towards having many smaller passes rather than sort of the large monolithic passes that we've historically had in the past. There is still this general categorization of things as front end and back end, but there's also a lot of phases that sort of lie in the middle. And so to some extent, the placement here is a little bit arbitrary, but we're going to attempt to categorize things a little bit in this course. So things like scanning and parsing are going to be considered front end. Things that involve the target language directly are generally going to be considered backend, and then there's going to be a lot of stuff that's sort of in the middle, and so we'll refer to those as middle end passes. So this will include things like static analysis, intermediate code generation, and some intermediate optimization. And like I said, the back-end passes are the ones that deal directly with the target language, like instruction selection, machine code optimization, register allocation, instruction scheduling, and finally assembling and linking. So the modern approach to this, again, uses a lot of little passes, even smaller than these. So the LLVM system, for instance, has dozens or hundreds of passes that happen during one compilation, and so these. This kind of framework is sometimes referred to as nano passes because it's a lot of very tiny passes that happen. And sometimes you repeat passes. Sometimes a pass can be redone after other passes and it has more work to do. So here is what the compiler that we're going to write is going to look like. So we start with the source code in the Decaf language. The first portion of the compiler, RP1, is going to be the lexing phase. So it's going to take that code and split it up into a bunch of textual tokens. After we have those tokens, we're going to arrange those tokens in a way that represents the meaning of the program as an abstract syntax tree. This process is called parsing. That's going to be the second major project. And then we're going to do static analysis to check this program to make sure that it's valid, and that's going to produce an annotated abstract syntax tree that has information about types and symbols. Once we have that information and we've verified that the program is correct enough to be able to generate some target code, we're going to generate an intermediate linear representation. So we're going to use iloc for this, and that'll be project 4. So that'll be now converting the program down into individual sort of machine code level instructions, although iloc is not a real machine code language, not like x86 or ARM or something like that. So once we have that, then we are going to need to get it to the point where we could actually run it on a real machine. And part of that involves decreasing the number of registers that we use down to a number of registers that could be physically located on a particular CPU. And so the final phase in our compiler is going to be register allocation, which is going to emit iloc again, but it's going to be a modified iloc that uses a maximum number of registers. Once we do that, then we will be able to do a very straightforward translation, and we're not going to implement this as a project. I'm just going to give this to you. But there's a very forward, simple translation from a linear, so from the allocated IR, or from the allocated iloc to y86, and that's going to be sort of the final endpoint. And then you can take the y86 and you can assemble it using the assembler from 261, and you can run it using your solution to P4 or the reference solution if yours didn't quite work out when you took 261. But in any case, that's the general framework. This is what we're going to be working towards all semester.